All right, good evening, everyone, and thank you for joining us for tonight's Scleral Education Society presented webinar. Tonight we have two of the experts in the industry, Langis, Michaud, and Dr. Lipson, talking about the science of sclerals, what we've learned from the latest research. So our two presenters tonight, first we have Dr. Michael Lipson. He is recently retired from his position as an optometrist and associate professor at the University of Michigan. His clinical practice involves specialty contact lenses, ortho-K, keratoconus, post-transplant, post-refractive surgery, and severe dry eye patients. He's published peer-reviewed clinical research studies on ortho-K, vision-related quality of life, myopia control, and new lens designs. He lectures nationally and internationally on all of those topics. He developed and validated questionnaire to assess vision-related quality of life for all types of vision correction, including ortho-K. He has authored chapters and textbooks on ortho-K, scleral lenses, and general contact lens topics. He is a consultant to the specialty contact lens industry, emphasizing ortho-K education. He is on the GPLI advisory board, serves as a vice president of the Scleral Lens Education Society, and is on the Scleral Lens Education Society board for many years. We also have Dr. Langis Michaud, who graduated from the University of Montreal College of Optometry in 1986, where he also obtained his master's degree in physiological optics. He is a full professor and practices at the University of Montreal since 2001 as the chief of the contact lens department. He is a fellow of the American Academy of Optometry and a diplomate, the British Contact Lens Association, the Scleral Lens Education Society, and the European Academy of Optometry and Optics. Dr. Michaud has published numerous articles in peer-reviewed journals and publications or professional reviews. He has often been invited to speak in Europe, Asia, and the United States. Finally, Dr. Michaud is the current president of the College of Optometrists of Quebec. And with that, I will turn it over to Langis to start the presentation.
Yes, thank you, and welcome to everybody to this webinar. And we will revisit tonight the terminology about scleral lenses. And with Michael, we'll help you to, in fact, adopt a common language to describe these wonderful devices that we prescribe on an everyday basis. Here are disclosures very rapidly. So the objective is certainly to become more familiar with the terminology that was recently adopted officially by the Scleral Lens Education Society and published in a peer-reviewed journal. Just as a basis, I know that everybody listening to this webinar knows what a scleral lens is, but we have to remember these basic facts, in fact, in order to understand the terminology associated with that. So lens is a big lens that vaults over the ocular surface, composed with a central zone, an intermediate zone, a limbal zone, and a landing zone. And as a final portion, the edges of that lens can be also modified. So the terminology we will recommend to you to use from now describe a scleral lens as a lens that is composed with these 5 different areas and or sections, and each of them can be described independently, but they are all linked in order to compose this scleral lens that will vault over the ocular surface. And one thing that we use as a term is the sagittal depth, obviously, and the sagittal height. These are 2 different elements that are most of the time confounded. We will talk about sagittal height for the ocular surface, but as for the lens, it will be the sagittal depth. And obviously, the sagittal depth of the lens should be a little bit higher compared to the sagittal height of the ocular surface to vault over that surface. And both are determined by the diameter we'll talk with of the cornea and or the ocular surface, or the cord we mentioned, and or as for the lens, the overall lens diameter. Yeah, as I mentioned, the sagittal height or depth, depending on if we're talking about the ocular surface of the lens, is determined by a chord, and the larger the chord is, or the larger the cornea or the ocular surface is, the larger the lens is, obviously the sagittal value will be increased. The steeper the curve of that, vaulting surface is, the higher the sag value is. And to the contrary, smaller diameter or flatter curves will be associated with reduced sag height or reduced sag depth, depending on if we talk about the ocular surface and the lens. And obviously this scleral lens vaulting over the ocular surface will be supported in part by a liquid reservoir, and that liquid reservoir should have, a determined height as well. The term clearance was used in the past, but we will suggest that it's no longer appropriate, and we'll talk about tear reservoir or fluid reservoir height to describe this over the entire cornea, and we can specify if it's over the central cornea or over the limbus. So it helps to really describe, in fact, what we are talking about, and just instead of just having multiple words to describe the same reality. And the ocular surface itself is very complicated. We learned from the last year's study and the published articles in the peer-reviewed journals that it's not only non-symmetrical surface, but it's more complicated than that. It's highly toric, and the if we are going away from the limbus, the farther the distance is, the more toricity you'll have in general, in average for that conjunctiva. But in this case here that is presented, it's a very regular pattern like we see in the cornea with two principal meridians and a very symmetrical astigmatism with high and lows curves along two principal meridians. But 70% of those corneas are not really like that. They are really not symmetrical, and we can describe the astigmatism of the conjunctiva as highly irregular. So this reality asks to describe this surface with specific terms that Michael will cover later on. So this paper published in the Journal of Contact Lens and Research and Science, it's free access available from the journal website, describe the ocular surface, just as mentioned, at a 16 millimeter chord, which is average of most of the scleral lenses prescribed and sold around the world. The conjunctiva is spherical just for 6% of the patients you'll meet. The toricity that is regular, just as I showed in the previous slide, is the reality for almost 30% of the patients. So that means that 65% of your patients that you see next morning in your exam chair will show at 16 millimeter asymmetric high and low points, and or will be affected with toricity that has a periodicity different from 180 degrees. That means that this surface is highly irregular, not really predictable. So you have to put a lens on that eye and to evaluate in every quadrant if it's fitting well or not. And or you can just map this conjunctival surface, as you saw previously with the topographer, corneal scleral topographer. There are two machines available in the market for that, and they are very, very in fact three with the Pentacam now, and you have the eaglet and the S-map. But these three machines will describe you this ocular surface. It will help you to customize your fit and to align the lens very nicely on the conjunctiva. And so we have really to pay attention to that surface. Obviously, if you use smaller lenses, which is the case for a lot of practitioners in North America and elsewhere in the world, let's say in a 15.5 millimeter diameter lenses, obviously you'll face a little bit less toricity, but it may be surprising. I have few patients showing a high level of toricity at the limbus, but you never know. You cannot predict just looking at this eye what will go on, and it's really not linked with the cornea itself. If you have a very highly toric cornea, that doesn't mean that the conjunctiva will be highly toric as well. And you have a very spherical cornea, that doesn't mean that the conjunctiva will be also spherical. So you have to evaluate with instrumentation and or with trial and error process with your lenses. But at the end of the day, you have to realize that most of these conjunctiva are highly irregular and should be described accordingly to that. So in summary, what do we need to describe a scleral lens? Obviously, we define the lens, any lens, from its base curve. Scleral lenses have base curve, and the base curve will dictate the power of the lens. If you with the similar lens you change that curve for a steeper curve, obviously it will change the volt as well. But the power of the lens will be changed just because the base curve is changed. But base curve, mostly in scleral lenses, is related to the power. And if you change any curve except the base curve, the power of the lens will remain the same. Sag value, but sag I mentioned, which sag, it's sag height or sag depth, depending, and sag from where. The overall lens diameter can dictate a sag value, but where the lens is landing on the conjunctiva is another chord that will dictate another, value for the sag. So you have to realize, where you are at and what kind of sag you want to describe, and you have to be as precise as you can to make the lab and the other practitioners in your office to exactly understand what you mean. Peripheral curves, again, Michael will explain what we suggested as the appropriate terminology to describe these curves. There are several words in the field from manufacturers, from design to design, but at the end, these peripheral curves are just there to align the lens with the ocular surface and to make it landing nicely on the conjunctiva. So we just summarized these peripheral curves with the 4 zones or 5 zones we described at the beginning, and hopefully it will be endorsed by anyone in the field to talk the same language as well. The back lens power is the regular power of the lens, obviously dictated by the refractive error of the patient. The tear layer or the fluid layer under the lens has a power as well. In gas-prone lenses, we know the lacrimal lens will have a certain amount of power that will modify the final lens, power itself. But in scleral lenses, it's even more important, because if you change the shape of this fluid layer under the lens, you will definitively change the overall power of the system over that surface. And certainly the lens power will have to be modified as well in order to compensate for these changes. So the back lens power of the lens is an important factor to consider, but it may be influenced by other factors in the lens fit. The lens diameter, the overall lens diameter, is one thing. We will talk a little bit later about the primary functional diameter. That is defined by where the lens is landing, but the lens diameter is habitually the overall lens diameters, 14.9, 15.5, 16, 18, 21, and depending on which lens you are working with. Material has to be specified as well. We now have, very high decay material, up to 200 value of decay. We have regular material with 150 or 100 decay material. So you have to tell the lab what kind of material you want to deal with. And obviously with scleral lenses, because these are thick lenses fitted with fluids underneath their surface, that may restrict at a given point oxygen delivery to the cornea. You want to have the highest decay possible in order to preserve and to protect the ocular health of that surface, especially on compromised cornea where the endothelium may be altered. So you have to specify the material you will use or you will prescribe, and you have to know the impact of the selection of this material when you order these lenses from your lab. And the overall lens thickness is very, very important. Lens thickness is determined by the power of the lens, for sure. Plus 20 lenses, as it is for soft lenses, gas perm lenses, even glasses lenses. Plus 20 will be thicker compared to a -2 lens, no question. But if you want to really help you in your fit and to reduce the mass of the lens and to improve the oxygen delivery to the cornea, then you may specify to the lab what kind of thickness you want to deal with. You know, the thinner the lens is, the better it is, in my experience. And certainly we cannot go under 200 microns because it will break. But you know, you can be around that 200, 250 microns. Many manufacturers or many practitioners will have a fear of lens flexure. We did some studies out of that, and it's not happening if you are well aligned in every quadrant. We fitted, you know, thin lenses with low fluid reservoir, and we fitted thick lenses with higher tear reservoir, and we evaluate the residual astigmatism after that, and there was no significant difference regardless of the lens diameter we use. So there's no real flexure that is occurring if you are over 200 microns of lens thickness. But you know, it's important, I think, to discuss with the manufacturers to get, you know, lenses as thin as possible, especially if you align well in every quadrant, to preserve and to promote ocular health over time. So you have to tell the lab what you want. You know, when the lab say to you, you know, we'll take care of it, thanks for your business, that's a very good attitude, and we are grateful to the consultant, because they know their stuff, they know their design, and the lab consultant is certainly your best friend at the end of the day. They can help you a lot, you know, and consult them. Please make these calls and email them and trust them, because they are really knowledgeable people with their design, and they know better than everyone, you know, how to help you with your difficult fits. But if you can talk the same language, it would be even better. If you can adopt the same terminology to describe what you see on the eye and what you want to have as a final product you will deliver to the patient, then obviously it's better. And hopefully with the publication of that official terminology from the Scleral Lens Education Society, we really want to have everybody in the field, you know, eye care practitioners, consultants, manufacturers, everyone interested in that field, to talk about, you know, the same language, and certainly to adopt the same terminology. Actually, what is missing is what we would want to know, and it's really depending on each particular proprietary design, is where the lens is intended to land. Because in my experience, again, we evaluate a few times in studies we did in Montreal, the impact of the lens diameter on several physiological aspects related to scleral lens wear. And most of the time, we don't find any difference between larger lenses and smaller lenses as for the impact. Let's take as an example the intraocular pressure increase related to scleral lens wear. We didn't find any difference between larger lenses and smaller lenses, despite the fact that intuitively we would think that a larger lens will be supported with, you know, a lot of conjunctiva, a lot more conjunctiva compared to a smaller one. But most of the lenses are designed with curves, and not tangent curve, but real curves. And the real diameter is where the lens is hitting the ocular surface. The rest is just plastic on the ocular surface. If you have a tangent design lens, and there are very few of them in the field, then the diameter may have an impact, and yes, you are more supported by the conjunctiva at that time. But you know, and generally speaking, for, you know, those practitioners in the field working with regular lenses we prescribe on a day-to-day basis, you know, the real overall diameter that you think you are dealing with is not the real diameter. Let's say that a 16mm lens is not a 16mm lens. In fact, if it hits the conjunctiva in the ocular surface at 14.9 or 15.2 or 15.8, millimeters. So that lens becomes a 15.2 millimeter lens, not a 16 or a 16.5, because this is where the lens is landing. So we have to know this information from the lab, and we have, as a practitioner, to determine if it's important for us to prescribe this lens or this other lens, depending on that piece of information that is actually missing. And hopefully, with time, we'll get that. Because part of the publication we did, and part of the recommendation we make to the manufacturer is that not only the terminology is important to talk about the same language, but also we have to we suggest a few elements that has to be provided by manufacturers to practitioners in order to help us to design better lenses and to have a better outcome with our patients. Same thing for intermediate curves and peripheries. Let's say that, you know, a flat one or steep one curve, or peripheries, flat one, steep one. From lab A, it may be meaning 30 microns. From lab B, it may be 50 microns, and the third lab is probably in the middle, 40 microns. So we have to adopt the same language again, and instead of flat and steep, we have to describe these changes and modifications step by step by the number of microns they generate on the surface. So we can compare apples to apples and oranges to oranges and design to design in order to better fit our patients. The thickness of the lens as well should be defined by their meridional thickness if it's changed over the surface. Most of the scleral lenses are not thicker at the center of the lens, but in the mid periphery, around 3 to 4 millimeter from the center. And this information is very important if you want to evaluate the potential impact on the physiology of the eye. The stabilization process, you know, if you design a front toric surface, what kind of stabilization process will the lab use? Is it double slab off? Is it, you know, toric periphery? Is it prism ballast? Yes, we have to really know that, and most of the time it's missing information we don't know, and it may play an important role in the final outcome, and every other element that are necessary to customize the lens fit and the lens design to our patient needs. So what we need, again, clinically from manufacturer, I just explained that. From the patient, we have to assess more accurately the surface. Topography, corneal topography is not necessary really to fit scleral lenses, because, you know, the cornea may be highly irregular. You have to look at the elevation map, yes, not the curves. You want to look at where the hot spots are, how irregular that surface is, where should I pay attention to vault over this very high surface. So the regular maps are not really useful. Elevation map is very, very useful, and other maps as well. But, you know, elevation is certainly one thing I'm taking good attention at. From the manufacturer, as I said, we have to know about their design and how to customize it. Talking to the consultant is a good thing, but having more information in hand make me more happy, because I really participate in the design of that lens, and I understand what I'm doing instead of just relying on someone else who will, you know, give me some medication about, you know, how to troubleshoot that particular patient. But at the end, it's an exchange, and we have to learn from each other, and we have to be better at what we're doing, but we have to understand what we're doing. And from the clinical experience, for sure, you know, clinical experience is certainly enhanced if I understand what I see, if I evaluate the patient more accurately, if I understand the design, and if I can talk with the same language with everybody involved. That's the magic word for tonight, you know, common language. And to adopt a common language is certainly one key message that we want to leave you with tonight. So this guide was published recently in Contactlens and Anterior Eye. If you have access to this journal, you can download the paper with the reference that is there. If I was an author of that paper, and Michael as well. So if you want to have a copy and you have not access directly from the website of this journal. Email us privately, obviously, and we can send you a PDF copy as an author of this article, and we can provide you with this valuable information. We will have a few examples in the following slide about, not bad, but somewhere and somehow misleading terminology. These are from abstracts published in the literature. And this is one example for this one here. Smaller mini-scleral lenses and a larger mini-scleral lenses. How come a mini-scleral could be larger? What is the size of that lens? I have no clue. And what is a smaller mini-scleral? Is it a regular GP lens? I don't know. It's certainly a scleral lens, so it walls over the surface, but is it a 15 millimeter lens, a 14? So I really don't know. So that type of terminology is confusing, and we have to adopt, better wording to describe what we're doing and what we are fitting.
I can start on the next one here, Langis.
Okay, go ahead, Michael.
So thank you for that good background. You set me up really well for all of the rest of this. But this is an example from some of the literature that we're seeing. And, in the abstracts, you can see some of the terminology that's used about estimating central clearance, post-lens tear reservoir, conjunctival compression. Those are all terminologies that are used. We're trying to look at another example like this when people are using things like flexural stress or the inner diameter landing point of the lens and compression. It's kind of confusing when we try to look at this and try to compare to what we're fitting in our own office. So I guess one more example here where the use, as Langis mentioned before, of a mini scleral contact lens and the mean sagittal depth. All of these things are rather confusing. So we're looking to try to get into some consistency on this. When people are using terminology like negative pressure. So it's something that we're trying to create some consistency so that we speak the same language. And so this is basically the reiteration of the publication that was just made, and you will also be able to find it here on the Scleral Lens Society website. That kind of terminology is still presented on the website there, and I think if you know how to get onto the Scleral Lens Society website, you have to be a member, but you can register for free and be able to have access to this information. And I guess the best, when we look at objectives and methods of this, the best way to think about this was very obvious to me when I just was traveling in Europe. And when you were traveling over there, we take appliances, we want to plug in our phone, and they have different receptacles or different charging methods in Europe, different plugs that are used. And so you have to have all the converters to do all this, and it gets rather confusing and somewhat a bit frustrating. But somebody in this high-tech world invented USB plugs, and these are universal, and they are everywhere around. So basically, if you have your USB and you have adapters for those, you can plug in anywhere. So what we're trying to get to here is to get to this common language and terminology that's used not only by the fitters, but by the labs and the publication people, the researchers. And to give you a little background, I mean, this idea was developed by the Scleral Lens Society and the board, the members committee, and they got together a number of experts in the field, as well as trying to coordinate with the ISO, the International Standards Organization in the US, about how to describe a scleral lens. And through a number of meetings that were in person, some over computer, basically it was finally adopted about a year ago, and finally got into print just this past few months. And the ISO requirements talk about norms and standards that really are not established for scleral lenses at this point, and needs to be revised, and we have Ralph Stone working on that with us, with the ISO. But this is in collaboration with the Scleral Lens Society and the guidelines, and we want to speak this common language. And in the general terminology, what's highlighted in red here on this is some of the things that we'll discuss today, but there's certainly a lot more out there. Many, many terms that are used to describe scleral lenses and scleral lens fitting. So if we start off with the word application, technically we apply the scleral lens onto the ocular surface. It's not inserted into the eye. We are keeping it on the surface of the eye, so we prefer to use the term application of the lens. The word insertion obviously is associated with many other things, but it is not appropriate really to insert a lens into the eye. We're applying it to the surface. When we talk about diagnostic scleral lenses, we had always used the word trial lenses, and they're really not trial lenses because we know that it's a lens that is made with known and specified parameters. So when we put that lens on a patient, we know how it is behaving at that point and how any modifications that we make should modify the fit to optimize it for that particular patient. So we know exactly all those terms that we were talking about before: the sagittal depth of the lens, the curves that are placed on the lens, the edge design, and based on those parameters, we can make adjustments to optimize the fit. Now, as Langis mentioned, when we talk about the lens, we're talking about sagittal depth of the lens. But when we describe the ocular surface, we're talking about sagittal height of that ocular surface. And it's always, there is not just one height of a surface. It has to be defined from a specific spot. In this case, we use what's called a chord diameter. We could describe it at a point on the cornea. We might say, okay, at a 10 millimeter chord, what is that height? And when we're talking about scleral lenses, though, they are landing beyond that limbus. So we're usually talking about a point somewhere beyond the corneal diameter, 15, 16, or even 18, 20 millimeters chord diameter. So again, when we're trying to describe the sagittal height of that ocular surface, we want to know the reference point on where we need to know that. And so the example given here is 3,800 microns at a 15 millimeter chord. And the acronym that we're using for this is OSHO, the overall sagittal height of the ocular surface. So when we talk about the sagittal height of the cornea, again, just as I mentioned before, we're talking about the cornea alone, and that would be at the limbus. And again, that would have to be specified for an individual patient, because we have some that are 12 millimeters, as in this example, but there's certainly other ones that might, a cornea that might be 11 millimeters, or another one that's 13, or anywhere in between. And the acronym that we're suggesting to be used for that is SHC, sagittal height of the cornea. And again, as I kind of mentioned before, when we talk about a scleral lens, we're not talking about a mini or a full scleral or anything else. We're talking about a scleral lens, and that was defined earlier as a lens that does not bear on the cornea. It clears the cornea and the limbus to bear its weight on the conjunctiva overlying the sclera. So again, as it's shown at the bottom of the screen, we want to eliminate the terminology of mini scleral or scleral contact lens or large scleral, etc., and eliminate these terms like SCCL or SCL, which is commonly referred to a soft lens, and just make it SL, scleral lens. Again, as Langis alluded to a minute ago, there was a lot of discussion about how to describe the thickness of the fluid beneath the lens. And again, the terminology that's been used in the past is down below here: lens clearance, fluid chamber, tear thickness. But to be most consistent, all of the discussions of all of the experts in the field came to the consensus that fluid reservoir would be the most descriptive term, because the fluids under there certainly are tears, but there are other things there. The solution that the lenses are applied with, non-preserved saline, any artificial tears, or even autologous serum, any other mixture of things, it's fluid. And that fluid remains between the lens and the eye during the whole time that the lens is being worn. And that fluid reservoir can be described in terms of its depth and its location. In other words, the examples here: a fluid reservoir of 300 microns in the central zone. We could get more specific than that, 3 millimeters from the geometrical center of the cornea, etc. Another way that we certainly want to be able to describe that fluid reservoir is over the limbus, how much fluid reservoir is between the lens and the limbus. And the terminology in the paper that you'll see is FR fluid reservoir. So for example, in a abstract that you would see where you'd see mini scleral contact lens to be comfortable, the mean wearing time, etc., corrected would replace the word mini scleral contact lenses to be plainly scleral lenses. I want to get to some more details about how do we describe the lens once we're seeing it on the eye in terms of quadrants, in terms of its lens orientation. And obviously we're familiar with this with other types of contact lens fitting, but when we talk about lens orientation, it's been common in the past to talk about nasal or temporal rotation, and that is based on soft lenses, because traditionally a lot of them have been marked in the 6 o'clock position. And so you could look at a marking on the lens and see if it's rotated on the right eye nasally or temporally, but you'd have to know which eye you were talking about. So to be more consistent, certainly we should talk about this lens in terms of clock direction, and it's very descriptive to talk about clockwise or counterclockwise rotation, and that applies exactly the same to the right and left eye. And above here, the acronyms of degrees of clockwise rotation or degrees of counterclockwise rotation. And if you remember, 1 clock hour on that is equal to 30 degrees. So just keep that in mind as you look at that. Another area that we want to describe is not just how it's fitting, but the lens design itself. And this is where a lot of the confusion comes in, because each manufacturer is using different terminology relative to each of these terms: the profile of the edge or the landing zone, localized vaulting, notches. All those things are terms that we came up with to say these are the most consistent and most descriptive terms to be used. So for example, we talked earlier about the 5 zones of a scleral lens. Can be summarized in 3 distinct zones. So there's an optical, a transition, and a landing zone. Now, there are other curves that are often placed on these lenses by various manufacturers, but again, we're going to go through this on a more general basis right now. On the edge profile, for example, we talk about the edge profile is in a plane containing that scleral lens axis described as standard, if not modified. What does standard mean? You know, each manufacturer has a different standard. So we would like to know and suggest that we talk about modifications in terms of microns, that a positive value of microns, that it says plus 50 microns, is moving away from the ocular surface, or thought to be flatter, flatter by 50 microns, for example. And negative values would be a minus 50 microns moving toward the ocular surface, or what might be called steeper. And the edge profile acronym we're suggesting is EP, edge profile. And very commonly we've seen this with manufacturers, that the terminology used now is flat 1, steep 2, etc. And again, each manufacturer may be different, the amount of microns. So we really don't know from one to the other. And that's essentially the purpose of all of this, is to try to say, how do we keep speaking the same language that means the same thing for any lens that we happen to be fitting on that patient? So we would suggest down below plus 50 microns to the edge, or minus 75 microns from 60 to 110 degrees in terms of quadrant specific edge design. This is a very, very important part of scleral lens fitting, where that lens lands, the landing zone, where it bears its weight. It's located just peripheral to that transition zone and begins at what we would call the primary functional diameter of the lens. And that primary functional diameter is what Langis referred to before as where that lens first lands and first contacts the ocular surface. And it can be a curvature, it can be a planar or flat surface subtended at an angle from that transition zone. But the acronym that we would use for this is the landing zone radius, or the landing zone width. And in the example of these planar surfaces, they're not curves, but angles, and specified at various angles. And certainly the landing zones can be broken down into 1, 2, or 3 of those, and they can be different in different meridians. Again, this is kind of a reiteration of the same thing, the edge flattening or steepening, to try to change how much that lens bears on the sclera or lifts away from the ocular surface. And again, it can be described spherical, toric, and various meridians. This last term, localized vaulting, is introducing something that we've been talking about when there are various obstacles in the sclera, raised or lowered areas where you have a localized area with different clearance. And certainly it can be specified in terms of its depth into the lens, its location relative to the edge of the lens, and its location relative to its position. And so it would be described as a width. It may be, as the example, 1 by 2 millimeters at 45 degrees, and it may be 1 millimeter from the edge, or 2 millimeters from the edge. Notches, similar thing, that these notches have to be located and stabilized so that they stay just in the right position. And again, Langis mentioned the stabilization process. And these are the acronyms that can be used in terms of prism ballast, double slab off, the asymmetric peripheral curves, or even a truncated lens. But SP would be the stabilization process. The transition zone, it's located just peripheral, obviously, to the optical zone, and people have called it a variety of things, a peripheral corneal zone or a limbal zone. But again, to be consistent throughout, its transition is from the optical zone to where the lens lands in that landing zone. And again, the lens can be raised or lowered at that point to optimize the fit. And there can be many transition zones, multiple ones. And a way to describe it is down below. Transition zone 1 is a 10.5 millimeter curve, and it's 0.4 millimeters wide. Now, this is the part that is something that really took a lot of discussion on our part, and probably one of the parts that I think has the greatest implications for determining overall success with lens. Not necessarily the thickness, but we talk about maximal edge thickness, maximal lens thickness. This is certainly important to know at various points in the lens, both for the function of the lens physically, but for the physiological response of the eye. Now, Langis introduced the idea that there are different lens diameters that are suggested in terms of the fitting, and there certainly is not one diameter that works well for every single patient. And we know what the overall lens diameter is, and it's the same concept as what we've been using with corneal lenses all these years. But down below, we introduce something called overall sagittal depth of the lens. Now, when you look at scleral lens from one manufacturer to another, you've obviously seen it, and each lens comes labeled. One may say it's a 4,000 micron sagittal depth. One may say it's a 5,000, 4,800, whatever. And those lenses, even two lenses from different manufacturers having the exact same label of, say, for example, on this one, 4,200, a 4,200 depth from one manufacturer may not fit the same way as a 4,200 from another. And what we're talking about here is consistency. We would like to know, as a fitter, what the overall sagittal depth of the lens is from edge to edge. That should be one of the important parameters that we know about this lens. And the OSDL should be labeled on that lens so you can know at this 18 millimeter overall diameter lens, what is that sagittal depth? If you lay it on a table, what is that sagitta? But just as important, and probably more important than that overall sagittal depth, is the primary functional lens diameter and the primary functional sagittal depth of that lens. So what we would like to propose as well is the adoption that each lens has its own design of where it's intended to land first, where it first contacts the ocular surface. And so this particular lens isn't labeled here, but say, for example, like the previous one, the overall lens diameter is 18 millimeters, but where it lands might be 15.5 or 16 millimeters. And for each lens that you receive, there should be on the label something that you can know where that lens is intended to land. The primary functional diameter of the lens. And this is kind of the demonstration at that functional diameter, what is the sagittal depth at that diameter? And again, that would be defined as that the chord where that functional lens diameter is, what the sagittal depth is at that point. So in this particular example, an 18 millimeter lens at 15.5 millimeters may have this primary functional sagittal depth of 4,100, whereas the whole sagittal depth edge to edge may be 4,800, 4,600. But again, to compare fitting characteristics from one brand to another, it would be nice to know, it would be very helpful to know this particular brand of lens and to compare it to another one. So you said this one is 4,100. If I took a 4,100 from another manufacturer, that you would at least have similar primary functional sagittal depth. So what is next basically is we would like everybody in the industry to adopt these guidelines. We'd like everybody to read them, become familiar with them, so that anybody who's writing about scleral lenses, speaking about scleral lenses, the educators training, the new practitioners, even the editors of these peer-reviewed journals should develop some consistency, as well as the manufacturers. That's the really important part, that we can get that information, and the manufacturers have that. They like to keep much of it proprietary, but it really would be beneficial to the industry as a whole if the manufacturers and the practitioners were able to speak the same language and be able to compare apples to apples here, so to speak. So that's our goal. The goal was to publish this in a journal, and we just did that. So we do have some time for questions. So
thank you, gentlemen, very much. Very educational lecture. A couple quick housekeeping items before we move on to the questions. We'll get an email tomorrow morning regarding this webinar. There'll be 2 links there. One is for an evaluation survey, which we turn into ARBO, that lets us know what you thought of the presentation, the content, and the setup, and lets us kind of tailor our future webinars accordingly. The other link will be a quiz you can take if you wish to receive COPE credit for attending this course. There's some information you need to include, including your OE tracker number and state license number on the link. You'll be prompted to do so. You'll have to get a 70% or better on that quiz to get credit. That's not our rule. That is ARBO's rule, unfortunately. And answers will be required by the 17th of this month. Again, all that information will be in an email going out tomorrow morning. Included with that email will be a copy of the video of this presentation, so you can go back and review it if needed before taking that quiz. So a couple questions here we have. The first one is, if they did not tell you the overall sagittal depth of the lens, where do you typically start? I guess in regards to just different fit sets on the market.
if you don't know what is that, Andrew?
It says if they don't tell you the overall sagittal depth of the lens, where do you start? And I guess they're just, where in general would you start if you don't have the sagittal height information of the lens? I guess it just depends on what the recommendation of the manufacturer would be.
That would be certainly one guideline if you don't know. Basically, most of them have a label on there which will have some kind of a sagittal depth, but it is not always known if that's an edge-to-edge sagittal depth or if it is a functional sagittal depth where that lens is intended to land. So normally one would say, well, if you have an average cornea, low cone, early cone, you might start kind of in the middle of that set, somewhere in the middle, and kind of bracket yourself from there. So some of the lenses do have guidelines to say, well, if you have a more advanced cone, you might start with the next higher depth lens. Or if you have a post surgical patient, post refractive surgery patient, you might start with a lens with a little less depth than the standard.
I would complete the information by the fact that based on the studies made in the Netherlands and across others research centers in Waterloo and Montreal, and so in fact there was 7 or 8 different research made on the normal sagittal height of the ocular surface at 15 millimeter cord, and the value, it's a highly variable from one patient to another patient, but the average is around 3,700 microns. So if you want to vault over that surface by 250 to 300 microns, that means that you are near the 4,000 SAG value as the go-to lens for the first lens for a 15 millimeter cord. If you want to go with larger chord, meaning larger lenses as well, probably, you have to increase that, because the larger the chord is, the higher the sag you'll have to adopt. So if you have a 16 millimeter lens, for example, to start on normal cornea, normal profile, or a low cone, 4,200 would be a good starting point. If you have a bulging cone or a cornea that is really higher than that, or a very large cornea, because large cornea will dictate higher sag as well. So you can start with 4,400. An oblate surface will ask for a 4,000 sag value as a starting lens. But you have to put that in balance. You can also use your topographer. If you go on the details of your topographic maps, you may have the sagittal height for a given chord. Let's say that you have a 10 or 11 millimeter chord, because most of the cornea will be under 12 millimeters. So depending on the quality of the topography, you may have some indication of the sagittal height at 10.5, 11 millimeter chord. But let's say 11 millimeter chord, you have 2,600. For every millimeter of increase, you will have 400 microns. That means that you have your topographer tell you that you have at 11 millimeter 2,600 microns. You want to fit a 16 millimeter lens, then you want to rise by increase by 5 millimeter that chord. 5 millimeter, every millimeter is 400 microns, so 2,000 on top of the 2,600 that you already have. So you start with 4,600 sag value as your go-to lens. So there are multiple ways to determine the go-to lens, and or just follow the manufacturer fitting guide. They are quite accurate for their design habitually.
Do you have other questions there, Andrew?
Yeah, there's a couple more here. Next one just says, how do you measure the PFD?
Well, right now we have no way of measuring that in our office. The PFD, the primary functional diameter of the lens, where it's intended to land, is variable by the manufacturer. You could call your lab and talk to the consultants and say, this is where it's intended to first land, and they would be able to give you that information. That's the best way I would know right now.
Very good. Looks like we have time for maybe one more. Basically, the question is, they find it tough to navigate some of the proprietary nomenclature used by different lens companies to describe their parameters. Any advice on helping one compare apples to apples when working with different manufacturers?
Do you want to take that, Langis? You want me to?
Yeah, in fact, for as it is for the primary functional diameter, every lab has their proprietary names, and they describe their lenses with very sophisticated and good marketing names to describe their lenses. I think the best way to start the discussion with them is to refer to the paper we published and ask them to comply with what we recommend and to provide you with the information we suggest. But if you reinforce the fact that it's important for you, most of the manufacturers will listen to their customers, I think, and they will begin to adopt the same terminology. And when a few labs will start the process, then the other will follow, no question. And certainly at the end will be all. Everybody will gain out of that, because we'll adopt the same language to describe the same thing. But for the moment, it's kind of far west over there, because some terminology is used for this lab, and that doesn't mean that the other lab using similar terminology describe exactly the same thing. That's why we just published that paper.
But it is definitely an area of confusion for practitioners, I would agree, and there are some of the labs that are just starting to use this terminology that we're suggesting, and some of the labs, they will not be able to answer the question if you ask them what is on the label of the vial of the lens that you were sent. Where is that sagittal depth measured from? What is the chord diameter that's measured from? And then Some will not be able to answer it. Some will tell you that it's edge to edge. Some will tell you that there is another measurement that's taken. But it is certainly an area of confusion for practitioners to try to compare that.
Well, gentlemen, thank you very much. It was a wonderful lecture. Thank you, everyone, for attending. We'll have another set of Scleral Lens Education Society webinars in 2020, so please stay tuned to your inboxes for information regarding those. Other than that, thank you again and have a good night.
Thank you.
Good night, everybody. Thank you.